Okay, here we're going to talk about the four functions that we introduced in the last lecture, namely internal energy, enthalpy, and the two new ones, Helmholtz free energy and Gibbs free energy. There are certain ways in which you can express these functions in terms of variables, and there are so-called natural variables that you can express these functions as a function of, and let's investigate that. So remember, when we were deriving criteria for spontaneity, for example, we had an equation like this, du minus TdS plus, that's an S, plus PdV is less than or equal to 0. And we got this by combining the first and second laws and assuming only PV work. All right, so you might review that lecture if this doesn't look very familiar. Let's, and just again, the equal sign, this less than or equal to sign, the equal sign means for a reversible process, and the less than sign is associated with an irreversible, which we call real process. Just to make things simple, let's now consider only reversible processes. That means we just put this equal sign. We don't have to keep carrying around the less than sign. So in that case, and then let's put these two terms over on the left-hand side. We have that the differential of u is equal to TdS minus PdV. Now let's look at this equation. This says that u is affected by changes in entropy and also by changes in volume. We're doing only PV work. So those are the two variables that change internal free energy. I don't know quite, did I say that, enthalpy? Internal free energy. And then you take that change in entropy and multiply by temperature, and then subtract off the change in volume times pressure, and then you got the change in internal energy. So I think hope I convinced you that U, for this particular case, only PV work, is a function of entropy and volume. So if we're going down this way, we'll say that S and V are natural variables for internal energy U. All right, now what we're going to do is to do some mathematical manipulations, use partial differentials, and derive some interesting relations here. So U is a function of entropy and volume. Let's take the total differential of U. That's how U changes with entropy at constant volume times the change in entropy, plus how U changes with volume at constant entropy times the change in volume. Now, we also have this relation between U, this is just what we said before, that du is TdS minus P dV. So let's look at these two equations. This particular, let's look at that. And let's look at that. Comparing the two equations, this implies that how U changes with S at constant volume is equal to temperature, and how U changes with volume at constant entropy is minus P. Now, that's something you wouldn't expect to find out normally, but actually, if you think about it, remember in the very first lecture we talked about pairs of variables, and S was paired with T and V was paired with P. So in a sense, these are how internal energy changes with entropy at constant volume, well, that would be related to temperature. And how U changes with volume at constant S, that you would think maybe would be related to pressure. And in fact, they are. I'll just jump here from our derivation last time. Enthalpy, and getting the equal sign, reversible process, is TdS plus PD plus Vdp. So this implies that H is a function of S, if S changes, H changes, and also P, if P changes. So these are the natural variables for H. We'll do the differential. dH is how H changes with S at constant P times ds, plus how H changes with pressure, second variable, constant first variable, times dP. Well, look at that, T, V. So T, definition of temperature, is how H changes with S at constant P, and V is how H changes with pressure at constant entropy. Again, PV and TS. All right, so that's an interesting relation. Just gives a new meaning to volume and temperature. Let's do it for Helmholtz free energy. In our derivation of the last lecture, we ended up with something like this, minus S dt minus P dV. So this means A is a function of T and V. Those are the natural variables for A. So let's take the total differential of A. So dA will be equal to how A changes with temperature at constant volume times dt, plus how A changes with that second variable, volume, at constant temperature times dV. And we just go back up here, minus S, okay, so this will be minus S, and this term, the dV term, will be minus P. And finally, let's look at Gibbs free energy, and then deriving the equation for spontaneity. We ended up with this equation. dG is Vdp minus S dt. So the natural variables for Gibbs free energy is pressure and temperature. Those are things that if they change, that will change free energy. So this implies that G is a function of pressure and temperature. Let's take the total differential there. That's how G changes with pressure at constant temperature times dP, plus how G changes with temperature at constant pressure times dt. And if we contrast and compare, that looks like volume. And if we look at this one, that looks like minus entropy. So because we were able to identify the natural variables of our four functions, we were then able to identify derivatives of those functions with respect to the natural variables with things that we can either measure in the laboratory, volume or pressure, or associate like entropy. So that's kind of cool. That's the kinds of things that a lot of people do with thermodynamics. Just play with equations, differentials, and so on, and end up with interesting relations, like how G, the Gibbs free energy, changes with temperature, constant pressure. That's the entropy. So if you measure, for example, G as a function of temperature at constant pressure, let's see, something like that, then the slope here is minus the entropy. That's interesting. All right, so let's go back to the slides here. This sort of summarizes what we just did here. And here's a nice summary table of all the relations between the derivative of those four functions u, h, a, and g with respect to their natural variables associated with another variable, another state variable. As an example of the kinds of things you can do with just taking partial derivatives and playing with the math, let's look at this. This is equation 426 of Ball. Where did that come from? Well, just let's see. This is if you follow along in Ball, but those of you who don't have the Ball textbook, I'll just start here. You start with the definition of G. G is defined as H minus TS, and H is defined as U plus PV. And that's a little hard to read there. U plus PV minus TS. Now, let's look at this. Volume and entropy. Okay, volume and entropy. Look at this down here. Volume and entropy. You can associate volume and entropy as derivatives with respect to G. So let's just go ahead and do that. So this is equal to U plus P, how G changes with how G changes with P at constant volume. Did I get that right? Let's go back here. Yeah, how G changes with P at constant temperature. Oh, almost right. As long as we're erasing, we'll erase those things too. All right, how G changes with, what did we say? Mental labs here. How G changes with P at constant pressure. How G changes with P at constant temperature. And now might as well just put that minus sign in there. Minus T, and now we can substitute in for entropy. The entropy is how G changes with T at constant P with a minus sign in there. So how G changes with T at constant pressure times A minus 1. So all we did was substitute in, see we have G over here, and substitute in there. So where are we going here? Well, we want to have du on the left and dg on the right plus derivatives of dg on the right. So let's put u is equal to g minus p, how G changes with pressure at constant temperature, minus, and anticipation of things here. Let's put the p on the other side here just to make it a little more easier. Put that over there, that comes to be a plus, plus how G changes with temperature at constant pressure times temperature. But that was a plus, and that was a plus, so this must be a minus. Minus, okay, so minus, minus, but then you're putting it over on the other side of the equation to isolate u. All right, now let's take the differential u, that would be just dg, minus how G changes with pressure at constant temperature. This is just some number, so you don't have to take the differential. That comes out of the differential times dp. How G changes with temperature at constant pressure times dt. So that's how one starts the definition, how one gets this equation 426 of Ball. Now let's derive an analogous expression for u, assuming you know the behavior of A, how A varies with temperature and volume. All right, so instead of U, we're going to do A. Here we did G. Let's now do A. Start with the definition. A is defined as U minus TS. And let's see, we have A. Well, let's go ahead and isolate U. We want an analogous expression. That's equal to A plus TS. All right, let's go back to our handy-dandy table. Here is A. And what do we have there? We have a T and an S. A. Looks like we're going to take a derivative with respect to temperature. All right, so minus S is how A changes with temperature at constant volume. So we're going to isolate that. That's equal to A plus T. And don't forget there was a minus sign there. How A changes with temperature at constant volume. Take the differential. du is dA plus, and we'll put the t over there. This is the constant, so, and that's a minus sign there. So I have to put the minus sign there. Okay, minus how A changes with temperature at constant volume times dt. So there's the analogous expression, how A changes with temperature at constant volume. Now if we look at the problem, it said, assuming one knows behavior of A is varies with T and V. Well, we really don't know. We don't have to know how it varies with V. In fact, you just have to know how it varies with T, temperature. All right, so those are the kinds of things that you can do using natural variables and partial derivatives. So we'll continue along this line in the next part of Lecture 8.